You wake up on Mars. You stretch, expecting a window view of red horizons stretching into forever. Instead, you are staring at a concrete ceiling 3 feet above your face, buried under 5 feet of crushed Martian rock, because the planet above you is trying to kill you with radiation you cannot see, cold you cannot survive, air you cannot breathe, and dust that would shred your lungs from the inside out. Every breath you take was manufactured by a machine. Every drop of water was recycled from your own waste. Every calorie you eat was grown under artificial light in a room the size of a parking space. This is not science fiction. This is what the science actually says. And it is far worse than anyone has told you. If you want to understand what daily life on Mars would genuinely feel like, and why the reality would crush most people's fantasy of a new frontier, go ahead and hit that like button and subscribe. It helps more than you know, and we have a lot of ground to cover. Now, get yourself comfortable. Let's begin. Close your eyes and picture yourself on Mars. You are probably imagining something beautiful. Red desert stretching to the horizon. A pale sky fading into dusk. Footprints in alien sand. Maybe you see a small outpost in the distance. Lights glowing from round windows. Maybe you imagine stepping outside in a sleek pressure suit, planting a flag, gazing across an untouched world. It feels like the American frontier. Or Antarctica. Or some remote desert on Earth where brave people go to test themselves against nature. The images in your head were put there by decades of movies, artwork, mission animations, and tech company promotional videos. They show astronauts walking freely across open terrain. They show greenhouses full of tomatoes. They show people staring out panoramic windows at Martian sunsets with something like peace on their faces. Now erase all of that. Every single frame. Because the actual science of what living on Mars would feel like has almost nothing in common with those images. And the gap between the fantasy and the reality is not small. It is enormous. It is the difference between imagining a campfire in the woods and waking up sealed inside a metal tube underground, where every molecule of air you breathe was manufactured by a machine that you personally have to keep running, on a planet that is trying to kill you in at least a dozen ways simultaneously, none of which you can see, and none of which ever stop. The problem begins the moment you consider stepping outside. Mars has an atmosphere. People hear that and think it means something. On Earth, atmosphere means weather, wind, blue sky, breathable air, protection. On Mars, atmosphere means almost nothing. The Martian atmosphere is roughly 0.6% as dense as Earth's at sea level. To put that in concrete terms, Earth's atmospheric pressure at sea level is approximately 101 kilopascals. On the surface of Mars, that number drops to about 0.6 kilopascals. That is not thin air. That is not high-altitude mountain air. That is functionally a vacuum. It is comparable to the pressure you would experience at approximately 100,000 feet above sea level on Earth, and well above the altitude at which human blood begins to behave in terrifying ways. There is a threshold in aerospace medicine called the Armstrong limit. It sits at roughly 63,000 feet above sea level on Earth, the altitude at which atmospheric pressure drops so low that water boils at the temperature of the human body. Above the Armstrong limit, the fluids in your tissues, your saliva, your tears, the moisture lining your lungs, would begin to vaporize. Not because the temperature is high, but because the pressure is too low to keep liquid water stable at 37 degrees Celsius. The surface of Mars is far beyond the Armstrong limit. If you stepped onto the Martian surface without a fully pressurized suit, the moisture in your mouth and eyes would start to boil within seconds. Your lungs could not function. Consciousness would last roughly 15 seconds before oxygen deprivation shut your brain down. Death would follow in under 2 minutes. This is not speculation. This is confirmed aerospace physiology established through decades of altitude chamber testing and pressure research. Now add the composition of what little atmosphere Mars does have. Roughly 96% of it is carbon dioxide. Nitrogen makes up about 2.6%. Argon accounts for about 1.6%. Oxygen exists only in trace amounts, approximately 0.16%. On Earth, oxygen makes up about 21% of the atmosphere. On Mars, you would asphyxiate long before the low pressure killed you. Carbon dioxide at high concentrations is directly toxic to humans. At levels above 5% in a breathing mix, it causes confusion, headaches, and rapid loss of consciousness. The Martian atmosphere is 96% carbon dioxide. Every breath you attempted to take would poison you before it starved you of oxygen. So the first and most fundamental truth about living on Mars is this: you cannot live on Mars. You can only live inside something on Mars. The planet's surface is not a difficult environment. It is a lethal one. There is no amount of acclimatization, no level of physical fitness, no degree of human toughness that changes this. Without a fully enclosed, mechanically pressurized, artificially oxygenated habitat, a human being on the surface of Mars is dead. Not struggling, not uncomfortable, dead. This means that every single moment of your existence on Mars takes place inside an artificial container. The habitat is not your home base from which you go out and explore the frontier. The habitat is your entire world. It is the only volume of space on the entire planet where your biology can function. Step outside that volume without a full pressure suit and functioning life support, and you die. Not in hours, not in minutes, in seconds. The boundary between life and death on Mars is not a mountain range or a weather pattern. It is a wall, a physical, engineered wall, sealed against a pressure differential that wants to rip it open from the inside out. Think about what that pressure differential actually means for the structure you live in. Inside the habitat, the air pressure needs to be at minimum, around 52 kilopascals, if you are using a low-pressure, oxygen-enriched atmosphere, similar to early spacecraft designs. More likely, habitats would aim for something closer to Earth standard, around 70 to 101 kilopascals, because lower pressure environments increase fire risk, require careful gas mix management, and create physiological complications over long durations. Outside, the pressure is 0.6 kilopascals. That means every square meter of your habitat wall is being pushed outward by a force of roughly 10 metric tons at Earth standard pressure. 10 metric tons per square meter. Pushing outward, constantly, every wall, every window, if you even have windows, every airlock seal, every pipe joint, every seam. This is not like a building on Earth, where the atmosphere pushes equally on both sides. This is like living inside a balloon surrounded by vacuum. The structure wants to explode outward. Every material is under tension. Every connection point is a potential failure. A crack the width of a human hair in a pressure vessel can whistle air out fast enough to drop internal pressure to dangerous levels within hours. A larger breach, a failed seal, a micrometeorite puncture, and you are looking at rapid decompression that could kill everyone inside before they reach an emergency mask. Engineers who design spacecraft and space station modules understand this intimately. The International Space Station has experienced small pressure leaks that required weeks of painstaking investigation to locate and seal, and the International Space Station operates in a microgravity environment, with the full support infrastructure of Earth's space agencies monitoring every system around the clock. On Mars, your habitat would be sitting on a surface subject to thermal cycling between roughly -70 degrees Celsius at night and perhaps -5 degrees Celsius during a warm afternoon at the equator. These temperature swings cause materials to expand and contract repeatedly, stressing joints and seals over time. The habitat would also be subjected to Martian dust, which is electrostatically charged and abrasive, working its way into every crevice and mechanism. And the nearest replacement part, the nearest repair crew, the nearest manufacturing facility is between 55 million and 400 million kilometers away, depending on where Mars and Earth sit in their respective orbits. Let that sink in. If a critical seal fails on your habitat at 2 a.m. Martian time, there is no calling for help. There is no emergency evacuation. There is no rescue helicopter. There is you, your crewmates, your toolkit, and whatever spare parts you brought with you. Communication with Earth takes between 4 and 24 minutes each way, depending on planetary alignment. A real-time conversation is physically impossible. If you send a distress message, you will wait at minimum 8 minutes for a reply, and that reply will be advice from engineers who cannot see your situation, cannot touch your hardware, and cannot do anything except talk you through a repair that you must execute yourself while your air slowly leaks into the Martian sky. This is the baseline. This is not the crisis scenario. This is every single day. Now consider how large your living space actually is. Early Mars habitats, whether proposed by NASA, ESA, or private aerospace companies, tend to converge on surprisingly modest dimensions. NASA's MOXIE experiment demonstrated oxygen extraction on the Perseverance rover. But the habitats themselves, based on designs like the CHAR-PR analog at Johnson Space Center, suggest a pressurized living volume of roughly 158 square meters, about 1,700 square feet, for a crew of 4. That is the size of a modest 2-bedroom apartment. Except this apartment contains your sleeping quarters, your kitchen, your exercise area, your medical bay, your laboratory, your food growing facility, your water recycling system, your air processing equipment, and your workspace, all in 1,700 square feet, for 4 people, for years. There are no hallways leading to other buildings. There are no parks outside. There is no opening the window for fresh air, because the air outside would kill you. There is no walking to a neighbor's habitat without first putting on a pressure suit, cycling through an airlock that takes several minutes to operate safely, crossing exposed terrain where radiation is bathing you and dust is coating your suit, entering another airlock at the destination, and then cycling back to a pressurized environment. Visiting a neighbor on Mars is a logistical operation. It is not stepping next door. This confinement would define every aspect of daily existence. You would eat in the same room where you work. You would sleep within arm's reach of the machinery that keeps you alive. You would exercise on the same small treadmill or resistance machine every day, in the same corner of the same module looking at the same walls. The sounds of fans, pumps, compressors, and recycling systems would be constant, because silence on Mars means your life support stopped working. Privacy would be minimal. Personal space would be measured in cubic feet, not rooms. After a week, you would know every scratch on every surface. After a month, you would know the rhythm of every mechanical cycle in the habitat. After a year, the walls would feel like they were closing in, because psychologically they are. And this habitat, this cramped artificial bubble, is not sitting in a gentle environment. The temperature outside swings are brutal. Mars has an average surface temperature of roughly -60 degrees Celsius. At the equator during summer, daytime highs might reach 0 degrees Celsius briefly. At night, temperatures plummet. Near the poles, winter temperatures can reach -125 degrees Celsius. Your habitat must maintain a stable internal temperature against these extremes, using heating systems that consume power constantly. Insulation helps, but thermal management on Mars is a continuous energy drain. The Martian atmosphere, thin as it is, does move. Wind speeds during normal conditions can reach 60 to 100 kilometers per hour. Because the atmosphere is so thin, these winds carry very little force, far less than equivalent winds on Earth. A 100 km per hour breeze on Mars would feel like a gentle push, but the wind carries something much more dangerous than force. It carries dust. Martian dust is extraordinarily fine, averaging about 3 micrometers in diameter. That is roughly 4% of the width of a human hair. These particles are small enough to remain suspended in the atmosphere for weeks or months. During major dust storms, which can grow to engulf the entire planet and last for months, the dust blocks so much sunlight that solar energy collection can drop by 80% or more. This dust is not ordinary sand. Analysis from Mars rovers and Martian meteorites has confirmed that it contains silica, iron oxides, gypsum, and critically, perchlorate salts at concentrations between 0.5 and 1% by weight. Perchlorates are a class of chlorine-oxygen compounds that are toxic to humans even in small amounts. On Earth, perchlorate contamination in drinking water at concentrations of just a few parts per billion triggers regulatory action. On Mars, the soil is laced with it. Inhaling even a few milligrams of Martian dust would exceed recommended safe perchlorate exposure limits on Earth. Prolonged inhalation of the silica component alone could cause silicosis, an incurable respiratory disease well documented in mining and industrial workers on Earth. A 2025 study published in GeoHealth compiled the known toxic components of Martian dust and concluded that the respiratory and systemic health risks of long-term dust exposure represent one of the most serious and underappreciated hazards of Mars habitation. This dust would get inside your habitat. Not in theory. In practice, Apollo astronauts on the Moon discovered that lunar dust infiltrated everything despite their best efforts. It clogged mechanisms, scratched visors, irritated eyes and throats, and caused respiratory symptoms after just short-duration surface stays. Martian dust is finer than lunar dust, and Mars has an atmosphere that keeps it suspended and mobile. Every time an airlock cycles, every time a suit is brought back inside, every time equipment is moved through the door, dust comes with it. Filtration systems would need to run constantly. Suit cleaning protocols would become one of the most important daily routines, and even with rigorous countermeasures, trace amounts of dust would accumulate inside the habitat over months and years, slowly increasing exposure risk for everyone living there. The suit itself deserves attention because it determines what going outside actually means. A Mars surface suit would not be the sleek, flexible outfit depicted in movies. It would be a pressurized, multi-layered, thermally insulated, radiation-mitigating, dust-resistant system weighing between 40 and 70 kilograms on Earth, which translates to roughly 15 to 27 kilograms on Mars due to the lower gravity. Every suit excursion would require pre-breathing protocols to avoid decompression sickness. If the suit operates at a lower pressure than the habitat, donning and doffing the suit would take time. Mobility would be limited by joint constraints, pressurization stiffness, and the sheer fatigue of working inside a wearable spacecraft. Gloves would be thick enough to limit fine dexterity. Visibility would be restricted to what the helmet visor allows. Every outdoor activity would be physically exhausting, time-limited by consumable air supply and constrained by the need to return to the airlock before resources run out. This is what going outside on Mars would actually mean. It would not mean opening a door and walking into the landscape. It would mean spending 30 to 60 minutes preparing your suit, cycling through an airlock, and then waddling across terrain in a bulky pressurized shell, while a timer counts down how many minutes of oxygen you have left before you must return. You would not linger to admire the view. You would be working against the clock, monitoring your suit's internal pressure, temperature, and air supply with every step. An unexpected suit malfunction outside, a torn glove seal, a cracked visor, a jammed joint, and your margin for survival shrinks to minutes. There would be no leisurely Martian strolls. Every trip outside would carry real risk, require real preparation, and leave you physically drained afterward. And here is something that almost no one considers about those excursions. Even when you are outside, you are not actually on Mars. Not in any sensory way a human being would recognize. You are inside your suit, looking at Mars through a polycarbonate visor. You never feel the wind on your skin, because the wind would kill you. You never touch the soil with your bare hands, because your hands would be exposed to vacuum and toxic dust. You never smell the air, because there is no air you can smell. You hear almost nothing from the landscape around you, because the Martian atmosphere is too thin to carry sound at any volume a human ear could meaningfully register. A person standing on the surface of Mars without a helmet would hear barely a whisper. The wind that moves the dust is a ghost. The panoramas that look so dramatic in rover photographs are wrapped in a silence unlike anything on Earth. Because even the quietest desert on our planet still has atmosphere enough to carry the murmur of its own wind. Every other frontier in human history, no matter how hostile, allowed the explorer to stand in direct sensory contact with the environment they had traveled to reach. Arctic explorers felt the cold bite their faces. Desert crossers felt sand between their fingers. Ocean voyagers tasted salt on their lips and heard waves breaking against the hull. The sensory experience of being there was part of the reward, part of what made the suffering and the distance feel meaningful. Mars denies you this entirely. The planet is always right there, under your boots, above your helmet, surrounding the habitat on every side, and you can never once make unmediated contact with it. You are always inside something. The habitat, the suit, the rover cabin, the airlock. There is no moment, not a single one, in an entire lifetime on Mars, where you simply stand on the planet the way you can stand in a forest, or on a beach or in a field, with nothing between you and the world but your own skin. You travel 225 million kilometers to reach a place and then experience it entirely through barriers. Mars is not a destination you arrive at. It is a destination you observe from inside, a series of nested enclosures, each one keeping you alive and each one keeping the planet out. Now zoom out and look at the terrain you would be observing through that visor. Mars is often described as Earth-like because it has mountains, valleys, and what appear to be dry riverbeds. This visual similarity is exactly what makes the planet so psychologically deceptive. Olympus Mons, the largest volcano in the solar system, rises 22 kilometers above the surrounding plain. Val S. Marin Aeris is a canyon system stretching over 4,000 kilometers long and up to 7 kilometers deep. These features look like Earth geology at a larger scale, which tricks the human brain into assuming the environment is somehow compatible with human life. It is not. The mountains have no breathable air at any altitude. The canyons have no liquid water. The riverbeds have been dry for billions of years. Mars looks like a desert you could survive in. It is actually a vacuum chamber shaped like a desert. This visual familiarity is one of the most dangerous aspects of Mars from a psychological and cultural standpoint. People look at photographs from Curiosity and Perseverance rovers and see rocky landscapes that resemble the American Southwest. They see sunsets. They see clouds. They see dust devils that look like the ones in Arizona. The brain processes these images through its Earth-based framework and concludes that Mars is harsh but habitable, like a very cold desert or a high mountain plateau. In reality, no desert on Earth, no mountain summit, no polar ice cap, not even the most extreme environment our planet offers, comes close to the hostility of the Martian surface. The driest spot in the Atacama Desert still has breathable air. The summit of Everest still has enough atmospheric pressure to keep your blood liquid. The coldest Antarctic winter still takes place under a protective magnetosphere and an ozone layer that blocks the worst solar radiation. Mars has none of these things. Not one. And yet, this visual familiarity is precisely what fuels the public fantasy that living on Mars would be like homesteading on a new frontier. It would not. There would be no open-air frontier. There would be a sealed box. There would be no exploring the wilderness. There would be carefully planned, time-limited, physically exhausting, risk-laden excursions in a pressurized suit. There would be no sky above your head. There would be a ceiling. Always a ceiling. The surface of Mars would be visible only through small reinforced viewports or camera feeds, because large windows represent structural vulnerabilities in a pressurized habitat, and radiation passes through glass just as easily as it passes through the Martian sky. The view you imagined at the start of this story, the red horizon stretching into forever, would not be your daily experience. Your daily experience would be the interior of a machine you maintain, a machine you depend on, a machine that separates you from an environment so hostile that a single systemic failure could mean death. That is what the first day would teach you. The surface of Mars is not a place you live on. It is a place you hide from, behind walls of metal and regolith and recycled air, hoping the engineering holds. But the atmosphere and the pressure and the temperature are only the most obvious dangers. They are the ones you feel immediately, the ones that announce themselves the moment you step outside. What comes next is worse, because you cannot feel it at all. It does not announce itself. It does not give warnings. It accumulates invisibly, silently, relentlessly every second of every day, whether you are inside or outside, awake or asleep. It passes through walls. It passes through your skin. It passes through your DNA. And on Mars, there is almost nothing standing between it and you. On Earth, you are shielded by two invisible systems so effective that most people never think about them once in their entire lives. The first is the magnetosphere, a vast bubble of magnetic force generated by the churning liquid iron core deep inside our planet. This magnetic field extends tens of thousands of kilometers into space, deflecting the majority of charged particles that stream outward from the Sun and inward from deep space. The second is the atmosphere itself, a column of gas roughly 100 kilometers deep that absorbs, scatters and blocks nearly all of the high-energy radiation that makes it past the magnetic field. Together, these two systems reduce the radiation reaching Earth's surface to an average of roughly 2.4 millisieverts per year from natural background sources. You absorb this dose without noticing. Your body's repair mechanisms handle it effortlessly. It is biologically trivial. Mars has neither of these protections, not partially, not in a weaker form. Effectively, not at all. Mars lost its global magnetic field approximately 4 billion years ago. The planet's core cooled and solidified, shutting down the dynamo process that generates a planetary magnetic shield. Some localized patches of remnant magnetism exist in the southern crust, leftovers from the ancient field frozen into rock, but these crustal remnants are weak, scattered, and cover only small regions. They offer no meaningful protection to a habitat or a human being on the surface. For all practical purposes, Mars is magnetically naked, fully exposed to the charged particle environment of interplanetary space. The atmosphere that remains is, as we established, less than 1% of Earth's density. Even this thin layer provides some radiation shielding, particularly against lower energy solar particles arriving at steep angles near the horizon, where the atmospheric path length is longest. But against the most dangerous forms of space radiation, the Martian atmosphere is nearly transparent. High-energy particles punch through it as though it barely exists. The combined effect of no magnetic field and almost no atmosphere means that the Martian surface receives a radiation dose that would be considered an emergency exposure scenario for any worker in the nuclear industry on Earth. The radiation assessment detector aboard the Curiosity rover has been measuring surface radiation on Mars continuously since 2012. The data confirms that the annual dose on the Martian surface is approximately 240 to 300 millisieverts per year from galactic cosmic rays alone, with additional spikes during solar particle events. To understand what that number means, consider that the average American receives about 3.1 millisieverts per year from natural background radiation. A chest X-ray delivers roughly 0.1 millisieverts. A full-body CT scan delivers about 10 millisieverts, and medical professionals consider even that dose worth monitoring over a patient's lifetime. The annual dose on Mars is approximately 80 to 100 times the natural background on Earth every single year, with no way to turn it off, no way to step out of its path, and no season or time of day when it stops. But the raw dose number does not capture the real danger, because not all radiation is equal. The radiation environment on Mars is dominated by two distinct threats, and both of them are far more biologically destructive than the radiation most people encounter on Earth. The first and more constant threat is galactic cosmic rays. These are not rays in the ordinary sense. They are particles, primarily protons, but also heavier atomic nuclei stripped of their electrons, accelerated to extraordinary energies by supernova explosions and other violent processes across the galaxy. Galactic cosmic rays include HZE particles, meaning high-charge, high-energy nuclei of elements like iron, silicon, and carbon, moving at significant fractions of the speed of light. When one of these particles strikes biological tissue, it does not simply pass through like an X-ray. It carves a dense track of ionization damage through every cell it crosses, shattering molecular bonds and leaving a corridor of destruction at the DNA level. A single HZE particle can damage or destroy hundreds of cells along its path. The body can repair some of this damage, but not always correctly. Misrepaired DNA is the origin of cancer. On Earth, almost no galactic cosmic rays reach the surface because the magnetosphere and atmosphere block them. On Mars, they arrive unimpeded. Approximately 0.7 millisieverts per day reaches the surface from galactic cosmic rays alone, and unlike solar radiation, galactic cosmic rays are constant. They do not follow a cycle. They do not peak and subside. They are the ambient background of interplanetary space, and they are there every second of every day, year after year, decade after decade. No amount of time spent on Mars reduces this dose. It simply accumulates. The second threat is solar particle events. These are sudden, intense bursts of energetic protons, ejected from the Sun during solar flares and coronal mass ejections. Solar particle events are less frequent than galactic cosmic rays, but can be far more intense over short periods. A major solar particle event can deliver hundreds of millisieverts in a matter of hours. Without adequate shielding, a person caught on the Martian surface during a severe event could receive a dose large enough to cause acute radiation syndrome, characterized by nausea, vomiting, immune system suppression, and in extreme cases, death within days or weeks. Earth's magnetosphere deflects the vast majority of solar particle energy before it reaches the upper atmosphere. Mars has no such shield. The MAVEN orbiter has confirmed that solar particle events strip material directly from the Martian atmosphere, and that the surface receives the full brunt of energetic proton flux during major solar storms. On Mars, a solar particle event is not an astrophysical curiosity observed by satellite instruments. It is a medical emergency requiring immediate shelter behind adequate shielding mass. Now consider the combined lifetime dose. NASA currently limits astronaut career radiation exposure based on a 3% increase in the risk of exposure-induced death from cancer, calculated at a 95% confidence interval. In 2022, NASA standardized this to a flat career limit of 600 millisieverts for all astronauts, regardless of age or sex. On the Martian surface, at approximately 240 to 300 millisieverts per year from galactic cosmic rays alone, a person would reach NASA's career cancer risk limit within roughly 2 to 2.5 years. And that estimate does not include the additional dose accumulated during the 6 to 9 month transit from Earth to Mars, during which the crew would also be exposed to the full interplanetary radiation environment without the partial shielding of even a thin planetary atmosphere. A 2013 study published in the journal PLOS One, using NASA's risk models, predicted that central estimates for radiation-induced mortality and morbidity on a Mars mission could exceed 5% and 10% respectively, with upper confidence intervals reaching near 10 and 20%. Additional risks to the central nervous system from HZE particle exposure may significantly increase these estimates further, but the biological data needed to quantify those risks precisely does not yet exist. We are, in a very real sense, proposing to send human beings into a radiation environment whose long-term neurological consequences we cannot fully predict. This is why the discussion of Mars habitation inevitably turns underground, not because underground living is exotic or futuristic, but because it is the only known way to reduce radiation exposure to manageable levels over years and decades. Regolith, the loose rock and dust covering the Martian surface, provides effective shielding against both galactic cosmic rays and solar particle events. But the relationship between depth and protection is not straightforward. A 2022 study published in the Journal of Geophysical Research modeled radiation dose as a function of depth beneath the Martian surface, and found something counterintuitive. The effective dose actually peaks at roughly 30 centimeters below the surface, not at the surface itself. This happens because galactic cosmic rays striking the regolith produce secondary particles, primarily neutrons, through nuclear interactions with the soil. These secondary neutrons scatter in all directions, including downward and sideways, creating a zone just below the surface, where the combined primary and secondary radiation dose is higher than on the exposed surface above. You would be worse off hiding under a thin layer of dirt than standing in the open. Beyond that 30 centimeter danger zone, however, dose drops steadily with depth. The same study concluded that safe long-term habitation, defined as annual exposure below 100 millisieverts, requires a regolith shield between 1 and 1.6 meters thick. At 2 meters of regolith coverage, the dose drops to levels that most radiation protection frameworks would consider acceptable for occupational exposure over a career. 3 meters or more approaches something closer to Earth normal background levels. This means that any habitat designed for permanent or long-duration occupation on Mars would need to be buried under at least 1 to 2 meters of crushed rock, or built inside a natural geological feature that provides equivalent mass shielding. Lava tubes, which are underground tunnels formed by ancient volcanic flows, have been identified in orbital imagery of Mars. Some of these tubes may be hundreds of meters in diameter, large enough to house entire pressurized structures inside them. The roof of a lava tube, depending on thickness, could provide sufficient radiation shielding without any additional construction. This has led multiple researchers and space agencies to propose lava tubes as potential sites for early Martian settlements. But lava tubes come with their own set of challenges. Their interiors are uncharted. The structural integrity of their roofs after billions of years of thermal cycling, seismic activity, and meteorite impacts is unknown. Accessing them may require navigating steep terrain or constructing entry tunnels. Building pressurized habitats inside them would still require all of the same engineering as surface habitats. plus the additional complication of working in an enclosed underground environment with no natural light and limited access points. A collapse, even a partial one, could be catastrophic in ways that surface construction would not face. The alternative is to build on the surface and then bury the habitat. This is more straightforward in principle, but enormously labour-intensive. 1 to 2 meters of regolith over an entire habitat structure represents hundreds or thousands of metric tons of material that must be excavated, transported, and placed. On a planet where every machine must be shipped from Earth or manufactured locally from raw Martian resources, this is not a weekend project. It is a major construction campaign requiring heavy autonomous machinery, reliable power, and months or years of robotic preparation before humans even arrive. Either way, the implication is the same. Long-term Martian living means living underground or under a thick blanket of rock. The romantic vision of domed habitats with panoramic views of the Martian landscape is not just impractical, it is radiologically suicidal. Glass and transparent polymers provide no meaningful shielding against galactic cosmic rays. A large window in a Martian habitat is a radiation entry point. Every hour spent in an unshielded or lightly shielded room is an hour of cumulative dose that moves you closer to the career limit, closer to measurably elevated cancer risk, closer to biological consequences that cannot be undone. Some researchers have proposed lead-based or water-based shielding panels built into habitat walls as an alternative to burial. Water is an effective neutron moderator, and a layer roughly 20 to 30 centimeters thick provides meaningful protection against both solar particles and some galactic cosmic ray components. Lead and other dense metals can block lower energy radiation but are extremely heavy to transport from Earth. These solutions can supplement regolith shielding for specific rooms, like sleeping quarters, where crew members spend the most time. The strategy would be to create a heavily shielded inner sanctum within the habitat for sleep and extended rest, while accepting somewhat higher exposure in work areas used for shorter periods. This approach trades total protection for practical livability, acknowledging that perfect shielding everywhere is impossible with early Martian infrastructure. But even partial shielding strategies require accepting a fundamental change in how humans relate to their environment. On Earth, you walk outside without thinking about ionizing radiation. On Mars, you would track your cumulative dose the way a diabetic tracks blood sugar, constantly, carefully, and with the knowledge that exceeding limits has consequences that cannot be reversed. Time spent in lightly shielded areas would be rationed. Outdoor excursions in pressure suits would be limited not only by air supply and physical fatigue, but by radiation budgets. You might be assigned a maximum number of hours per week outside the shielded zone. Every activity outside the heavy shielding would carry a measurable biological cost, and the mission medical officer would track it against your lifetime allowance. This is the hidden architecture of Martian daily life, not the grand engineering of domes and rovers, but the quiet accounting of absorbed dose. A spreadsheet somewhere would track every crew member's cumulative millisieverts, ticking upward with every hour spent in the wrong room, every sortie to the surface, every solar storm that catches someone in a lightly shielded corridor. Radiation does not announce itself. There is no pain, no warmth, no sensation. You feel perfectly fine while the damage accumulates at the molecular level, rewriting the odds of your long-term survival with each passing week. And now we must return to the dust, because radiation and dust are not separate problems on Mars. They are entangled, and together they form a compounding threat that makes the surface environment more hostile than either danger alone. We established earlier that Martian dust averages roughly 3 micrometers in diameter and contains toxic perchlorates, silica, iron oxides, and gypsum. But the full hazard profile is worse than a simple list of ingredients suggests. The 2025 GeoHealth study we discussed earlier, led by researchers at the University of Colorado and the University of Southern California, went further than simply listing toxic compounds. The problem is not any single compound. The problem is the combination of particle size, chemical toxicity, exposure duration, and the impossibility of fully excluding dust from a pressurized habitat. 3 micrometer particles are classified as respirable dust, meaning they penetrate deep into the lungs, past the bronchi, into the alveoli where gas exchange occurs. Particles this small are not efficiently cleared by the body's normal defense mechanisms. They lodge in lung tissue and remain there. Over weeks and months, they trigger inflammatory responses that can lead to fibrosis, the buildup of scar tissue in the lungs that permanently reduces respiratory capacity. This is precisely the mechanism behind the silicosis we described earlier. Once lung tissue is scarred, it does not regenerate. And on Mars, unlike in a mine on Earth, you cannot walk away from the exposure at the end of a shift. Martian dust contains abundant silica, the same compound responsible for silicosis on Earth, but it also contains perchlorates at concentrations that multiply the hazard. Perchlorate salts are soluble and biologically active. When inhaled, perchlorate dissolves in the moist tissue of the lungs and enters the bloodstream. From there, it interferes with iodine uptake in the thyroid gland, disrupting hormonal regulation. Chronic perchlorate exposure is associated with thyroid dysfunction and at higher levels, aplastic anemia, a condition where bone marrow fails to produce adequate blood cells. On Mars, inhaling even a few milligrams of dust delivers perchlorate exposure that exceeds the safe thresholds we established earlier by orders of magnitude. And unlike waterborne contamination, inhaled perchlorate bypasses the digestive system entirely, entering the bloodstream through lung tissue with no filtration step in between. The dust also contains nanophase iron oxides, which give Mars its red color and also make the particles magnetic and electrostatically charged. This electrostatic charge is not a minor nuisance. It means the dust actively clings to surfaces, fabrics, seals, visors, and skin. It does not simply brush off. Laboratory simulations of Martian dust adhesion confirm that particles this fine and this electrostatically active bond to fabric, metal, and polymer surfaces at the molecular level, resisting removal by brushing, blowing, or vibration. Standard suit cleaning techniques developed for lunar operations would be insufficient against a dust that is finer, more chemically reactive, and continuously resupplied by an atmosphere that keeps it mobile. Martian dust shares every mechanical nuisance of lunar dust and adds chemical toxicity on top. The airlock ingress path we described earlier means that no amount of suit cleaning protocol or contamination barrier fully eliminates the transfer of fine particles into the habitat interior. Over months and years of regular surface operations, the concentration of Martian dust inside the habitat would gradually increase despite every countermeasure. This means the crew would face chronic low-level exposure to a substance that is simultaneously an abrasive, a respiratory toxin, a hormonal disruptor, and a carcinogen. On Earth, workers exposed to comparable hazards wear respirators, undergo regular medical screening, and are removed from exposure if symptoms develop. On Mars, there is nowhere to be removed to. The exposure is the environment. It is permanent. Dust storms amplify these problems dramatically. Mars experiences regional and occasionally planet-encircling dust storms that can persist for weeks or months. During a global dust storm, the solar dimming we described earlier escalates from a technical inconvenience into a survival crisis. The habitat's ability to run life support systems, water recyclers, oxygen generators, heating systems, and air filtration drops in direct proportion to the energy it can no longer collect. The same dust storm that threatens your power supply is simultaneously coating your solar panels with a layer of fine particles that further degrades their output even after the storm passes. Cleaning solar panels on Mars would be a regular, labor-intensive maintenance task. One more entry on an already overwhelming list of things that must be done to prevent slow degradation of the systems keeping you alive. The 2018 global dust storm on Mars provided a vivid real-world demonstration. NASA's Opportunity rover, which had operated for nearly 15 years, lost contact during the storm when dust accumulation on its solar panels dropped power below survival thresholds. The rover never recovered. Opportunity was a machine with no biological needs. A human crew facing the same power loss would be watching their oxygen generation slow, their water recycling falter, their heating systems struggle, all while trapped inside a sealed habitat with no ability to fix the fundamental problem until the storm passes and the panels can be cleaned. Nuclear power sources like radioisotope thermoelectric generators or small fission reactors would eliminate the solar dependence, but they introduce their own mass, complexity, shielding requirements, and failure modes. Now layer these two threats together and see how they interact. Radiation forces you underground or behind heavy shielding. Dust follows you inside regardless of how carefully you manage airlock protocols. The shielding that protects you from radiation also traps you in a confined space where dust accumulates. The same suits that protect you from the vacuum and the cold also serve as vectors, carrying dust back into the habitat. The power systems that run your air filtration are vulnerable to the dust storms that generate the particles you are trying to filter. Every mitigation strategy for one problem creates a dependency or vulnerability to the other. This compounding is what makes Mars so fundamentally different from any hostile environment on Earth. In Antarctica, the cold is severe, but the air is breathable and radiation is low. In a submarine, the confinement is extreme, but the hull protects you from pressure, and there is no toxic dust. In a mine, the dust is dangerous, but you can leave at the end of your shift and breathe clean air. On Mars, every major hazard operates simultaneously, all the time, reinforcing the others and leaving no dimension of the environment where a human being can simply exist without active mechanical intervention. The dust also degrades the equipment you depend on for survival. Fine abrasive particles work their way into mechanical joints, seals, bearings, and electrical connectors. They coat optical sensors and camera lenses. They reduce the efficiency of thermal radiators. They create electrical short circuits in exposed wiring. Every system exposed to Martian dust requires more frequent maintenance, more frequent replacement of parts, and more robust engineering tolerances than the same system would need in a clean environment. This maintenance burden is not theoretical. It is a confirmed observation from every rover that has operated on the Martian surface. The machines we have already sent to Mars have been degraded by dust in exactly these ways, and they do not breathe, do not have lungs, and do not need to keep their internal environments sterile. For human habitation, the dust problem extends beyond health and into the integrity of the habitat itself. Seals designed to maintain pressure must also resist dust infiltration. Airlock mechanisms must cycle reliably despite particles jamming moving parts. Filters must capture particles down to 1 micrometer or less without clogging so frequently that replacement becomes unsustainable. Ventilation ducts, heat exchangers, and humidity management systems must all function in the presence of fine particulate contamination that would trigger shutdown protocols in any terrestrial cleanroom. The engineering is not impossible. Humans are remarkably good at building systems that work in harsh environments, but every additional requirement adds weight, complexity, failure modes, and maintenance hours. On Mars, where resupply takes years and spare parts cannot be ordered from a catalogue, every added system is another thing that can break, another thing that must be monitored, another demand on a crew whose time and energy are already consumed by the basic act of staying alive. This is the reality that now comes into view. Radiation and dust are not dramatic, cinematic threats. No one will make a blockbuster about a crew quietly tracking their cumulative millisievert count or replacing an airlock seal gasket for the 4th time this month. These are slow, grinding, invisible burdens that accumulate day after day, month after month, year after year. They never spike into a single crisis dramatic enough to make a movie trailer. Instead, they erode the margins of safety, millimeter by millimeter, until the space between survival and failure becomes thinner than the dust particle lodged in your airlock seal. And the truly unsettling part is that radiation and dust are still only 2 entries on a much longer list. Because even if you solve shielding, even if you manage dust contamination, even if you accept the chronic exposure risks and budget your lifetime dose, and replace your filters and bury your habitat under meters of regolith, you still have a problem that never goes away, not even for a single hour. You still have to manufacture every molecule of oxygen you breathe. You still have to produce or recycle every drop of water you drink. You still have to grow or reconstitute every calorie you eat. You still have to generate every watt of power that keeps the lights on, the heaters running, the air circulating, and the machines functioning. And every single one of those systems must work correctly, continuously, without interruption. Because on Mars, a broken life support chain does not mean discomfort. It means death. And the nearest spare part is somewhere between 6 months and 2 years away, drifting through interplanetary space in a cargo pod that may or may not arrive on schedule. That is where this story goes next. into the machine itself, into the systems that would have to run perfectly, forever, with no margin for failure, on a planet that degrades everything it touches. Every environment on Earth, no matter how extreme, gives human beings at least one thing for free. In the Arctic, the air is breathable. In the deep ocean aboard a submarine, nuclear reactors provide effectively unlimited power. In the Sahara, you can find water if you dig deep enough, and the sun provides warmth and energy without any mechanical intermediary. Even the summit of Everest, where supplemental oxygen is often necessary, still offers atmospheric pressure high enough to keep your blood in a liquid state and gravity that your skeleton evolved to handle. Every hostile environment on our planet withholds some necessities while providing others. Survival becomes a problem of bridging specific gaps. Mars gives you nothing, not one thing. Not a single input required for human survival exists in a usable form on the Martian surface. The air cannot be breathed. The water is locked in subsurface ice or bound inside mineral structures and must be extracted by machine. The soil is toxic and cannot grow food without extensive processing. The sunlight is weaker, intermittent, and arrives through an atmosphere that provides no thermal insulation. The temperature is lethal without heating. The pressure is lethal without containment. Every single requirement of human biology must be manufactured, recycled, monitored, and maintained by engineered systems running inside a sealed habitat, every single one, simultaneously, without interruption. For as long as anyone remains on the planet, this is what transforms Mars habitation from an engineering challenge into something closer to a permanent emergency. On the International Space Station, life support is complex, but it operates within reach of Earth. Resupply missions arrive every few weeks. Spare parts can be launched on relatively short notice. Real-time communication with ground control is possible. If a critical system fails, there are contingency plans that include, as a last resort, evacuation in a Soyuz or Crew Dragon capsule that can return the crew to Earth's surface within hours. None of these safety nets exist on Mars. A supply mission from Earth takes between 6 and 9 months to arrive, and launch windows occur only every 26 months when planetary orbits align. If a critical component breaks 3 months after the last supply window closes, you wait roughly 2 years for the replacement, assuming it was identified, manufactured, loaded, launched, and landed successfully. In the meantime, you improvise or you die. Start with oxygen, because without it, everything else becomes irrelevant within minutes. The Martian atmosphere is 96% carbon dioxide. Oxygen exists only as a trace gas at 0.16%. You cannot extract breathable oxygen from the ambient air by any simple filtration process. You must break molecular bonds to liberate oxygen atoms from the compounds that contain them. The most direct approach is electrolysis of water, splitting water molecules into hydrogen and oxygen using electrical current. This is well understood chemistry. Submarines and the International Space Station use electrolysis systems to generate oxygen from water. But the process requires 2 inputs that are themselves difficult to obtain on Mars: water and electricity. We will address both of those shortly. An alternative approach is direct carbon dioxide electrolysis, splitting the abundant atmospheric carbon dioxide into carbon monoxide and oxygen. NASA tested this concept with the MOXIE instrument aboard the Perseverance rover. MOXIE successfully demonstrated carbon dioxide electrolysis on the Martian surface, producing oxygen at a rate of approximately 6 grams per hour during its test cycles. 6 grams per hour. A resting adult human consumes roughly 840 grams of oxygen per day, which works out to about 35 grams per hour. A single MOXIE unit at its demonstrated output could supply roughly 17% of one person's oxygen needs. Sustaining a crew of 4 would require a system producing at least 140 grams per hour, more than 23 times MOXIE's demonstrated rate, running continuously, 24 hours a day, every day, with 0 downtime. Scaling MOXIE's technology is theoretically feasible. The unit was a technology demonstration, not a full-scale production system. Larger electrolysis units with higher throughput could be built. But scaling introduces every problem that scaling always introduces: greater power demand, more heat generation requiring thermal management, larger and heavier components that must survive launch and landing, more complex plumbing and gas handling, and more failure points in a system that cannot tolerate failure. A 23-fold increase in output is not a simple multiplier applied to an existing device. It is a complete redesign with its own development cycle, testing requirements, and failure modes. An oxygen generation is not a system you run once and forget. It runs every minute of every day. If it stops for 8 hours, your habitat's internal oxygen concentration begins to drop. If it stops for 24 hours with a crew of 4 in a modestly sized habitat, carbon dioxide levels rise to dangerous concentrations, while oxygen levels fall toward the threshold where cognitive impairment begins. If it stops for 48 hours, you're in a medical emergency. The margins are not generous. Life support is not a background process on Mars. It is the foreground of existence, the single most important mechanical function occurring at every moment, and everything else, every scientific objective, every exploration goal, every construction project, is secondary to keeping it running. But oxygen generation is only half of the atmospheric equation, because the habitat does not just need oxygen added, it needs carbon dioxide removed. 4 human beings produce roughly 4 kilograms of carbon dioxide per day through normal respiration. In a sealed habitat with no natural ventilation, that gas accumulates. At concentrations above 1%, carbon dioxide causes headaches and impaired cognition. Above 5%, it becomes acutely dangerous. Carbon dioxide scrubbing systems, using chemical absorbents or regenerative processes, must run continuously alongside oxygen generation to keep the breathing atmosphere within safe limits. These scrubbers consume power, produce waste heat, and require their absorbent media to be replaced or regenerated on a regular schedule. A scrubber failure does not give you days of warning. It gives you hours before the air you are breathing begins to quietly poison you. And the first symptom, impaired judgment, is precisely the symptom least likely to be recognized by the person experiencing it. Humidity control adds another layer. 4 human bodies exhale moisture, perspire, and release water vapor from cooking and hygiene. In a sealed volume, this moisture accumulates rapidly. Excess humidity promotes microbial growth on surfaces, corrodes electronics, fogs, sensors, and viewports, and creates conditions for fungal contamination in food production areas. Dehumidification systems must extract and reclaim this moisture continuously, feeding it back into the water recycling loop. The habitat's atmosphere is not a passive medium you breathe. It is a managed industrial gas mixture, actively maintained in composition, pressure, temperature, and humidity by interlocking systems that all depend on each other and all depend on power. Now consider water. An adult human requires approximately 2.5 to 3 litres of drinking water per day under moderate activity levels. In a sealed habitat where water is also used for food preparation, hygiene, medical procedures, and crop irrigation, the total demand per person rises significantly. The International Space Station recycles approximately 90% of its water, recovering moisture from cabin air humidity, processing urine, and reclaiming wastewater from various systems. A Mars habitat would need to match or exceed this recycling efficiency, because the alternative, extracting new water from the Martian environment, is energy-intensive and mechanically complex. Mars does have water, but not in conveniently accessible form. Orbital and rover observations have confirmed subsurface water ice at high latitudes and in some mid-latitude regions, buried beneath anywhere from a few centimeters to several meters of regolith. Extracting this ice requires excavation equipment capable of digging through frozen, compacted Martian soil, followed by heating the excavated material to melt and collect the water, followed by filtration to remove perchlorate salts and other contaminants before the water is safe for human use or crop irrigation. Each step in this chain requires power, machinery, and maintenance. The excavation equipment must function in extreme cold, with abrasive dust working into every joint. The heating systems must operate efficiently in an environment where ambient temperatures hover around negative 60 degrees Celsius. The filtration systems must reliably remove perchlorates to parts per billion levels, because even trace perchlorate contamination in drinking water poses long-term thyroid and hematological risks. Water can also be obtained from hydrated minerals in the regolith, but extraction yields are lower and energy costs are higher. Atmospheric water vapor is another theoretical source, but Mars's atmosphere contains only about 10 to 20 precipitable micrometers of water, an almost negligible amount that would require processing enormous volumes of thin Martian air to recover meaningful quantities. For practical purposes, subsurface ice mining is the most viable source, and it requires a robust, continuously maintained industrial operation just to produce the most basic substance a human body needs. Once obtained, every drop of water enters a closed-loop system that must function with near-perfect reliability. Water recycling on the International Space Station has experienced repeated maintenance issues, including mineral buildup in processing lines, biofouling in storage tanks, and sensor malfunctions that required crew intervention. These problems were manageable with Earth-supplied spare parts and real-time ground support. On Mars, the same malfunctions must be solved with whatever tools and materials are on hand, and the consequence of prolonged water system failure is dehydration leading to incapacitation within days. The relationship between water and oxygen is also critical. If you generate oxygen through water electrolysis, every litre of water you split for oxygen is a litre you cannot drink, wash with, or use for crops. The two most essential resources for survival compete with each other for the same feedstock. This creates a resource allocation tension that must be continuously managed. Use too much water for oxygen, and you dehydrate your crew and your food supply. Conserve too much water and your atmosphere becomes oxygen poor. Balancing this equation is not a one-time calculation. It shifts daily based on crew activity levels, crop growth cycles, atmospheric leakage rates, and the efficiency of recycling systems that degrade over time. Food is the third leg of this survival tripod, and in many ways it is the most daunting. You cannot ship enough food from Earth to sustain a permanent settlement. A single person requires roughly 2,000 to 2,500 calories per day. For a crew of 4 over a 2-year surface stay, that is roughly 3 to 4 metric tons of food. For a permanent or long-duration settlement, the mass becomes prohibitive even with the most optimistic launch cost projections. Self-sufficiency in food production is not an aspirational goal for Mars habitation. It is an absolute requirement for anything beyond a short-duration visit. Growing food on Mars means growing it inside pressurized, artificially lit, climate-controlled modules. The Martian surface receives far less solar energy than Earth does, and what little arrives passes through an atmosphere that provides no greenhouse warming. Growing crops under natural Martian sunlight is theoretically possible in pressurized transparent enclosures, but those enclosures would need to be radiation shielded, thermally insulated, and large enough to produce meaningful yields. More practically, crops would be grown under LED lighting powered by the habitat's energy systems, in hydroponic or aeroponic setups that deliver nutrients directly to plant roots in water-based solutions rather than soil. Martian regolith cannot be used as agricultural soil in its native state. The perchlorate concentrations alone would make any food grown in unprocessed Martian dirt toxic. The regolith also lacks the organic matter, microbial communities, and nutrient profiles that terrestrial soil provides. Before Martian dirt could be used for plant growth, it would need extensive washing to remove perchlorates and other toxic salts, supplementation with nitrogen and phosphorus-based fertilizers, and inoculation with microbial cultures to establish nutrient cycling. This processing is possible in principle, but it adds yet another layer of industrial activity to the daily workload of a settlement whose primary occupation is already keeping its own life support running. The crop selection for Mars agriculture would be severely constrained. High-calorie, fast-growing, space-efficient plants would dominate. Potatoes, soybeans, wheat, rice, lettuce, and a limited selection of vegetables. Dietary variety, which is important for both nutrition and psychological well-being, would be minimal. Animal protein would be nearly impossible to produce at scale. The resource cost of maintaining livestock, even small animals like chickens or fish, in terms of feed, water, atmospheric load, waste management, and space, is vastly higher per calorie than plant cultivation. A Mars settlement would almost certainly be vegetarian by necessity, not by choice. Crop failure on Mars carries existential stakes. On Earth, a failed harvest means importing food from elsewhere. On Mars, there is no elsewhere. A contamination event in a hydroponic bay, a lighting system failure, a pathogen that destroys a crop cycle, or a miscalculation in nutrient delivery could wipe out weeks or months of food production. Backup food reserves would need to be maintained, but those reserves would be finite and slowly depleted if production shortfalls became recurring. The psychological weight of watching your food supply shrink with no way to replenish it from outside would be unlike any stress most humans have experienced. Waste management deserves its own mention, because no one talks about it, and on Mars it would consume significant crew time and system resources every single day. A crew of 4 produces biological waste continuously. Human waste must be processed, not simply stored, because in a sealed habitat it represents both a health hazard and a resource. Urine must be fed into the water recycling system. Solid waste must be dried, sterilized, and either stored, composted for potential agricultural use, or broken down chemically. Food scraps, plant trimmings from the hydroponic bays, packaging residue, worn-out filters, contaminated clothing, broken equipment, all of it must go somewhere. And on Mars there is no landfill, no garbage truck, no sewer system leading anywhere beyond the walls. Every waste stream must be managed internally. Composting generates gases that must be vented or scrubbed. Sterilization requires heat, which requires power. Storage consumes volume that a small habitat cannot spare. An overlooked waste management failure could introduce pathogens into the water system, contaminate the food supply, or generate toxic gases in a sealed, breathing environment. On Earth, sanitation infrastructure is invisible. On Mars, it would be a daily, hands-on, crew-intensive operation that no one signed up for but everyone depends on. Now, beneath all of these systems, supporting every one of them, is power. Everything on Mars runs on electricity. Oxygen generation, water extraction and recycling, food production lighting, heating, air circulation, dust filtration, communications, computing, robotic systems, suit charging, airlock operations, and every instrument and tool in the habitat. Without continuous, reliable electrical power, every other system fails in sequence. Solar power is the most readily available energy source on Mars, but it comes with severe limitations. Mars receives only about 43% of the solar energy per unit area that Earth receives, due to its greater distance from the Sun. The thin atmosphere means less atmospheric scattering, so direct sunlight on a clear day is reasonably useful for solar panels. But Martian days are roughly the same length as Earth days, meaning solar panels produce power for only about half the day. Nighttime requires battery storage or an alternative power source. And as we discussed, dust storms can reduce solar irradiance by 80% or more for weeks at a time, making solar power unreliable precisely when heating demands are highest, because dust storms also reduce surface temperature, and heating is not a minor entry on the power budget. It is one of the largest. At night and during dust storms, temperatures plunge far below that already brutal average. The habitat must maintain an internal temperature of roughly 20 to 22 degrees Celsius for human comfort and equipment function. That is an 80-degree temperature differential that must be sustained across every square meter of exterior surface, continuously through a structure that is in direct thermal contact with frozen ground below and near vacuum above. Insulation reduces but cannot eliminate the thermal loss. Every hour of every Martian night, heat bleeds out of the habitat into an environment that is functionally a cryogenic sink. Dust accumulation on exterior thermal surfaces reduces their efficiency over time. Ice formation at structural interfaces where warm interior air meets cold exterior walls creates condensation risks that can corrode metal, degrade insulation, and promote microbial growth inside wall cavities. Heating a Mars habitat is not like heating a house in Minnesota. It is like keeping a warm room inside a walk-in freezer that never turns off and occasionally drops to temperatures that would liquefy atmospheric gases on Earth. The power budget for a 4-person Mars habitat has been estimated at roughly 40 to 100 kilowatts of continuous generation capacity, depending on the level of in-situ resource utilization activity. For context, a typical American home uses roughly 1.2 kilowatts on average. A Mars habitat would consume power equivalent to roughly 30 to 80 American homes, and it must do so continuously, On a planet where the most abundant energy source is intermittent and vulnerable to planetary-scale weather events, nuclear fission systems offer a solution. NASA's Kilopower project demonstrated a small fission reactor concept capable of producing 1 to 10 kilowatts of electrical power continuously, regardless of dust, darkness, or season. Scaling this to the 40 to 100 kilowatt range a habitat requires is an active area of development. Nuclear reactors offer reliability and independence from solar conditions, but they add mass, require radiation shielding of their own, generate waste heat that must be managed, and introduce failure modes involving radioactive materials in an already hazardous environment. A reactor malfunction on Mars would combine a life support power failure with a potential radiological contamination event in a sealed habitat with no evacuation route. The most likely power architecture for early Mars habitation would combine solar arrays with battery storage and one or more nuclear units, providing redundancy. But redundancy itself has a cost. Every duplicate system adds mass that must be launched from Earth, occupies volume inside or adjacent to the habitat, requires its own maintenance, and consumes crew time that is already stretched thin. Redundancy is essential. It is also expensive in every currency that matters on Mars: mass, volume, time, and human attention. This brings us to the thread that connects every system described above: maintenance. On Earth, we live inside systems we barely think about. The electrical grid delivers power. The water treatment plant delivers clean water. The grocery supply chain delivers food. The atmosphere delivers oxygen. When something breaks, a specialist arrives to fix it, usually within hours or days, using parts sourced from a global manufacturing network. We are so embedded in this web of invisible support that we forget it exists. On Mars, every one of these systems is contained within the walls of your habitat, and the specialist who fixes them is you. There is no grid, there is no supply chain, there is no calling a technician. Every pump, every valve, every filter, every sensor, every seal, every circuit board, every motor, every gasket in the habitat is something that the crew must understand, monitor, diagnose, and repair. The maintenance burden of a Mars habitat would be unlike anything most people can imagine, because the number of systems that must function simultaneously is extraordinary, and the consequence of any single system's prolonged failure ranges from severe discomfort to death. To understand what daily life would actually feel like, walk through a single morning. You wake to an alarm in a room the size of a closet, under artificial light tuned to simulate dawn because there is no window and no actual sunrise reaches your sleeping quarters beneath a meter of regolith. Before breakfast, you check the atmospheric monitoring panel. Oxygen level, carbon dioxide level, humidity, pressure, trace contaminant readings. You note that the carbon dioxide scrubber in Module 2 is running 3% above its normal power draw, which could mean a degrading absorbent bed or a fan bearing starting to fail. You log the reading. You check the water recycling dashboard. Throughput, purity metrics, filter pressure drop. One filter is approaching replacement threshold. You note it. You check crop status in the hydroponic module, nutrient pH, reservoir temperature, light cycle timing, leaf coloration on the soybean rack. 2 potato plants show early signs of a calcium deficiency. You adjust the nutrient mix. You check battery charge state and solar array output. Yesterday's dust deposition reduced panel efficiency by 4%. Someone will need to clean them today. You check the radiation log. The cumulative crew dose for the week is within budget. All of this happens before you eat your first meal, which is a rehydrated grain porridge and a small serving of greenhouse lettuce. The same meal you ate yesterday and the day before, because the crop cycle only produces variety in slow, staggered rotations. This is not a bad morning. This is a normal morning. A bad morning is one where 2 of those readings are in the red instead of the yellow, and you have to choose which emergency to address first. Consider the failure cascades that become possible. A dust storm reduces solar output by 60%. Battery reserves begin depleting faster than anticipated. The crew reduces power consumption by shutting down non-essential systems, but heating is essential, air circulation is essential, oxygen generation is essential. Water recycling can be temporarily paused, but not for more than a day or two before hygiene and drinking water supplies become critical. Crop lighting can be reduced but not eliminated without killing plants mid-growth cycle, destroying weeks of food production. The crew begins rationing. Power reserves continue dropping. A secondary failure occurs. A water recycling pump seal, stressed by perchlorate mineral deposits, begins leaking. The crew must now divide their attention between power management and water system repair, using tools and spare parts from a finite inventory in a habitat where every hour of reduced air filtration increases dust contamination in the breathing air. This is not a disaster movie. This is a plausible Tuesday on Mars. The planet does not attack with a single dramatic catastrophe. It erodes your margins through dozens of small simultaneous stresses that individually seem manageable, but collectively overwhelm the crew's capacity to respond. A seal degrades. A sensor drifts out of calibration. A filter clogs earlier than expected. A battery cell underperforms. A crop develops a fungal infection. None of these alone is fatal. Together, they consume every hour of every day in reactive maintenance, leaving no time for the scientific work or exploration that supposedly justified the mission in the first place. The crew time budget is one of the most underappreciated constraints of Mars habitation. On the International Space Station, astronauts spend a significant fraction of their working hours on maintenance tasks, replacing filters, repairing equipment, managing inventory, conducting system checks. Studies of International Space Station crew time allocation show that maintenance and housekeeping routinely consume 40 to 50% of available work hours. On Mars, this percentage would likely be higher because the systems are more numerous, the environment is more degrading, spare parts are scarcer, and the consequences of deferred maintenance are more severe. A Mars crew would not be explorers who occasionally fix things. They would be maintenance technicians who occasionally explore. The inventory problem deserves its own mention. Every spare part on Mars must be shipped from Earth at enormous cost, or manufactured locally using in situ resource utilization techniques that are themselves in early stages of development. 3D printing using Martian regolith or recycled materials could eventually produce some replacement parts, but the range of materials and precision achievable with early Martian manufacturing would be severely limited. Critical components like pressure vessel seals, electronic circuit boards, precision sensors, and medical equipment cannot be fabricated from raw dirt and recycled plastic. These items must be anticipated, packed, launched, and landed intact months or years before they are needed, based on failure predictions that may not match actual conditions. If a component fails that was not anticipated, or if the spare is damaged during landing, or if the failure occurs after the spare has already been used for a previous repair, the crew faces a gap in their supply chain that cannot be closed for years. Improvisation becomes not a sign of ingenuity, but a daily survival requirement. The history of space exploration is full of celebrated moments of improvisation. The Apollo 13 carbon dioxide filter fix, the repair of the Hubble Space Telescope's flawed mirror, the creative solutions devised by Mars rover teams to work around hardware failures. These moments are celebrated precisely because they are exceptional. On Mars, they would be routine. The exceptional would become the expected, and the crew would live in a permanent state of creative problem-solving under existential pressure. Communication delays compound every maintenance challenge. When an International Space Station astronaut encounters an unfamiliar equipment failure, they can call Houston and receive expert guidance within seconds. With the signal delay we established earlier, a simple question and answer exchange can consume an hour. A complex troubleshooting session that would take 30 minutes with real-time communication could stretch across an entire day of back-and-forth messaging. During a genuine emergency, this delay is not merely inconvenient, it is potentially fatal. The crew must be trained to handle a vast range of failure scenarios autonomously, which means every crew member must carry an extraordinary depth and breadth of technical knowledge. They must be plumbers, electricians, mechanics, chemists, botanists, medical practitioners, and systems engineers all at once, all the time. The cumulative psychological weight of this maintenance burden is a story of its own, and we will get to it. But even in purely mechanical terms, the picture is clear. Living on Mars would not mean waking up and deciding how to spend your day. It would mean waking up and triaging which failing system needs attention first. It would mean tracking oxygen output rates, water recycling efficiency, battery charge levels, filter saturation indicators, crop health metrics, and radiation dose accumulations before breakfast. It would mean understanding that every system in the habitat is aging, that every seal is one thermal cycle closer to failure, that every filter is 1 gram closer to saturation, and that the gap between your current spare parts inventory and the next possible resupply shipment is measured in years. This is what the phrase living on Mars actually refers to when you strip away the promotional imagery and the aspirational language. It refers to living inside a machine, not beside a machine, not with the help of a machine, inside one. The machine is your atmosphere. The machine is your water. The machine is your food. The machine is your warmth. The machine is the barrier between your blood staying liquid and your blood boiling in your veins. And you are the machine's mechanic, its operator, its monitor, and its most vulnerable component, all at once, every day, for as long as you remain on a planet that provides you with nothing and degrades everything you brought with you. The engineering is extraordinary. The human capacity to design and build these systems is one of the most remarkable things our species has ever attempted. But engineering does not change the fundamental equation. On Mars, human life is not sustained by an environment. It is sustained by an apparatus. And the moment that apparatus falters, the environment is waiting on the other side of every wall, patient and absolute, ready to reclaim the space that human engineering borrowed from it. Cold, airless, irradiated, and completely indifferent to whether anyone inside survives the night. But systems can be built. Systems can be maintained. Hardware can be improved. Redundancy can be deepened. Resupply chains can be shortened as technology advances. The engineering challenges, immense as they are, exist within the domain of problems that human ingenuity has historically been able to solve, given enough time and resources. What cannot be engineered so easily is the thing that matters most. The human being trapped inside all of this machinery. The body that slowly changes in an alien gravitational field. The mind that watches the same walls for years without relief. The social bonds that fray under permanent confinement and unrelenting stress. The biology that was shaped across millions of years of evolution for a planet that is 355 million kilometers away and getting farther every day. That is where this story arrives next. Not at the limits of engineering, but at the limits of the human animal itself. Everything we have discussed so far can be drawn on a blueprint. Pressure vessels can be engineered. Radiation shielding can be calculated. Oxygen systems can be scaled. Water recyclers can be improved. Power architectures can be made redundant. Food production modules can be optimized. Every threat described so far in this story exists within the domain of physics and engineering, which means it is at least theoretically solvable given enough resources, time, and ingenuity. But there is a category of problem that no amount of hardware can fully address, and it is the category that may ultimately determine whether human beings can genuinely live on Mars or merely survive there in a state of permanent biological and psychological decline. That category is the human body and the human mind, neither of which was designed for this planet and neither of which can be redesigned to fit. Start with gravity, because gravity is the one environmental variable that cannot be engineered around inside a surface habitat. You can manufacture air, you can recycle water, you can shield against radiation, but you cannot increase the gravitational pull of a planet. Mars has a surface gravity of approximately 0.38 G, roughly 38% of what your body experiences on Earth. This means that every structure in your body that evolved under Earth, gravity, every bone, every muscle, every connective tissue, every fluid distribution pattern in your cardiovascular system would exist in a mechanical environment it was never built for. And unlike microgravity, which has been studied extensively aboard the International Space Station, the long-term effects of partial gravity on human physiology are almost entirely unknown. This distinction matters enormously. Decades of research in microgravity have documented a clear and alarming set of physiological changes. Astronauts on the International Space Station lose roughly 1 to 2% of their bone mineral density per month in weight-bearing bones like the hip and spine. Muscle mass declines, particularly in the legs and lower back, despite rigorous daily exercise regimens lasting 2 hours or more. Cardiovascular deconditioning occurs as the heart adapts to pumping blood without the assistance of gravitational return from the legs. Intracranial pressure increases as bodily fluids shift headward, contributing to a condition called spaceflight-associated neuroocular syndrome that can damage vision. Immune function appears to be altered. Wound healing may be impaired. These effects are well documented at 0G. What happens at 0.38 G is largely a guess. The critical question is whether 38% of Earth's gravity is enough to prevent, slow, or merely delay these degenerative processes. Recent research offers fragments of an answer. A 2026 study from the University of Rhode Island, Harvard Medical School, and several international partner institutions exposed mice to varying gravity levels aboard the International Space Station using an onboard centrifuge. The group exposed to 0.33 G, close to Martian gravity, showed that this partial gravity mitigated spaceflight-induced muscle atrophy, compared to full microgravity, but did not fully prevent it. Full prevention of muscle deconditioning was observed only at 0.67 G, roughly 2/3 of Earth gravity. The implication is sobering. Mars gravity may slow muscle loss, but is unlikely to stop it entirely. Crew members living on Mars for years would likely experience progressive muscular weakening that exercise alone might not fully counteract. Bone loss presents an even more uncertain picture. A 2022 study, using a simulated partial gravity environment, found that osteoblast function, the cellular process responsible for building new bone, was significantly inhibited at simulated Mars gravity. Critically, the study observed a threshold effect. Bone-forming cell activity was substantially impaired at 0.38 GeD, and this impairment was not dramatically worse at lunar gravity or microgravity. In other words, even a moderate reduction in gravity appeared sufficient to disrupt the fundamental mechanism of bone maintenance. If this finding translates to living humans, which remains unconfirmed, it means that Mars gravity might offer far less skeletal protection than its 38% figure intuitively suggests. You might lose bone at a slower rate than in 0G, but you would likely still lose bone, month after month, year after year, with no way to restore Earth gravity to halt the process. The consequences of chronic bone loss extend beyond fragility. Bones are not just structural supports, they are mineral reservoirs and blood cell factories. Bone marrow produces red blood cells, white blood cells, and platelets. Significant bone loss can impair these hematological functions, weakening the immune system and reducing the blood's oxygen-carrying capacity. On a planet where radiation is already challenging the immune system, and where every infection or injury carries amplified risk due to limited medical resources, any additional compromise to immune function is genuinely dangerous. Cardiovascular adaptation to partial gravity is another open question. On Earth, your heart works against gravity to push blood upward from your legs to your brain. In microgravity, this work is unnecessary, and the heart gradually deconditions, becoming smaller and weaker. At 0.38 G, the heart would still need to work against some gravity, but significantly less than on Earth. Whether this reduced workload leads to clinically meaningful cardiac deconditioning over years or decades is unknown. No human being has ever lived in partial gravity for more than a few days during the Apollo lunar surface missions, and those missions were far too short to reveal long-term cardiovascular adaptation. We are proposing to send people to live for years in a gravitational environment that no human cardiovascular system has ever been tested against, and we have no reliable data on what will happen. Fluid redistribution is another concern. In microgravity, the absence of gravitational pull allows bodily fluids to migrate headward, causing facial puffiness, nasal congestion, and elevated intracranial pressure. This fluid shift contributes to the neuroocular syndrome that has damaged the vision of a significant fraction of long-duration International Space Station crew members. At Martian gravity, the fluid shift would be less severe than in microgravity, but whether it would be absent is uncertain. Even a partial elevation of intracranial pressure sustained over years could contribute to progressive visual impairment, headaches, or more serious neurological consequences. On Mars, an ophthalmologist is not available, a neurologist is not on call. If your vision degrades, Your treatment options are whatever medications and simple interventions the habitat's medical kit contains. Now, extend this uncertainty across a lifetime. The first Mars settlers might be healthy adults in peak physical condition. But human settlements, if they are to be permanent, eventually include children. And this is where the gravitational question becomes truly uncharted. No mammal has ever been conceived, gestated, born, or raised in partial gravity. We do not know how a fetal skeleton would develop at 0.38 g. We do not know whether fetal circulatory patterns would form correctly. We do not know whether neurological development, which depends in part on vestibular input from the inner ear's interaction with gravity, would proceed normally. We do not know whether a child born on Mars could ever safely visit Earth, where the gravitational force on their bones, muscles, and cardiovascular system would be roughly 2.6 times what they had experienced their entire lives. A child raised on Mars might be permanently confined to Mars, not by choice but by physiology. Their body would be shaped by a world they could never leave. This is not speculation about the distant future. It is a direct consequence of the physics of settlement. If humans go to Mars to stay, the question of reproduction in partial gravity becomes unavoidable within a generation, and we currently have no answer to it. We have fragments of animal data, theoretical models, and an enormous void where human evidence should be. We would be conducting the experiment on actual children, in real time, with no control group, no ability to intervene if development goes wrong, and no way to bring the subjects back to Earth gravity if the results are harmful. The ethical dimensions of this are staggering and almost entirely absent from popular discussions of Mars colonization, and the confinement to Mars may not be limited to those born there. Even healthy adults who arrive from Earth and spend multiple years on Mars would undergo physiological adaptation to 0.38 GeG. Their bones would thin, their muscles would weaken, their cardiovascular systems would recalibrate to a lower workload. After 3 years, 5 years, a decade, their bodies would no longer be Earth bodies. They would be Mars bodies, shaped by reduced gravity in ways that might be partially reversible but almost certainly not fully. Returning to Earth would mean subjecting a gravity-adapted body to 2.6 times the gravitational load it has grown accustomed to. The re-entry and landing forces alone could cause injury to weakened bones. Standing upright under full Earth gravity could produce syncope as a deconditioned cardiovascular system fails to maintain adequate blood pressure to the brain. Walking could risk stress fractures in a skeleton that has shed years of mineral density. Mars settlement may become a one-way journey, not because of launch windows or fuel costs, but because the body quietly crosses a threshold beyond which return becomes medically dangerous. The settlers would not be trapped by technology. They would be trapped by biology. Set aside the body for a moment and turn to the mind, because the psychological burden of Mars habitation may be the most underestimated dimension of the entire enterprise. NASA's CHAR-PR program is currently conducting its second analog mission, with 4 volunteers confined inside a 1,700 square foot simulated Mars habitat at Johnson Space Center in Houston for 378 days. The first mission, completed in July 2024, provided early data on the psychological effects of long-duration confinement with realistic Mars conditions, including communication delays of up to 22 minutes each way. Crew members from the first mission reported what might sound like trivial complaints, but carry profound weight in the context of permanent settlement. They missed green grass, they missed blue sky, they missed feeling fresh air on their faces, they missed the sensory richness of a living world, which is nearly 3 times the cruising altitude of a commercial airliner. These are not luxuries, they are inputs that the human nervous system evolved to require. The human brain did not develop in sealed metal enclosures. It developed in open landscapes filled with variable light, wind, temperature shifts, biological diversity, distant horizons, and an atmosphere of natural sounds. Decades of environmental psychology research have established that access to nature, even through a window, measurably reduces stress, improves cognitive function, and supports emotional regulation. Confinement in small, monotonous, artificially lit spaces produces the opposite: elevated cortisol, disrupted sleep, impaired concentration, increased irritability, and progressive emotional flatness that researchers sometimes call the third quarter phenomenon, a well-documented decline in morale and performance roughly 3/4 of the way through a long-duration isolated mission. On Mars, the third quarter phenomenon would have no resolution because there is no end date. Analog missions on Earth, no matter how realistic, operate with a fundamental psychological safety net. The crew knows they will leave. They know that outside the habitat, Earth exists in all its sensory richness, and in a defined number of months they will walk back out into it. This knowledge, even when suppressed, shapes every psychological response to confinement. On Mars, that safety net does not exist. There is no walking outside without a pressure suit. There is no fresh air, ever. There is no blue sky, ever. There is no green landscape, ever. The sensory deprivation is not temporary. It is the permanent condition of existence. Light itself becomes a subtle but relentless adversary. In a habitat buried under regolith for radiation protection, there is no natural sunlight, no sunrise gradually warming the walls, no shift from morning blue to afternoon gold to evening amber. The lighting inside would be artificial, and much of it would be optimized for crop growth rather than human circadian biology. LED arrays tuned to maximize photosynthesis produce a spectrum that is measurably different from the full spectrum light the human brain uses to regulate its sleep-wake cycle. Submarine crews, Antarctic winter rover teams, and shift workers in windowless facilities all exhibit circadian disruption when deprived of natural light cues, manifesting as fragmented sleep, daytime fatigue, impaired immune function, and mood disorders. On Mars, this disruption would be chronic and inescapable. The crew could install dedicated circadian lighting systems that simulate daylight patterns, and this would help, but a simulated sunrise in a sealed underground room is not the same stimulus as actual sky. The brain knows the difference, even when the conscious mind does not. Over months and years, the absence of genuine natural light would add yet another slow biological stress to a body already contending with reduced gravity, elevated radiation, and chronic confinement. The Mars 500 study, a 520-day isolation experiment conducted in Moscow between 2010 and 2011, observed significant behavioral changes in its 6-person crew, including disrupted sleep-wake cycles, reduced activity levels, and measurable changes in stress biomarkers including cortisol, serotonin metabolites, and dopamine levels. One crew member experienced a persistent depressive episode, another became progressively withdrawn. Interpersonal conflicts emerged and were managed through deliberate social protocols, but the strain was real and documented in physiological as well as psychological data. These analog studies lasted 1 to 1.5 years. Mars settlement means decades. It means watching the same walls and the same faces, not for a mission duration but for the rest of your life. It means knowing that the person you had a conflict with at breakfast is the person you will eat dinner with tonight, and tomorrow night, and every night, because there are only 3 or 4 or 6 other humans within 100 million kilometers. Social friction that would be trivial on Earth, where you can take a walk, visit a friend, change your environment, becomes inescapable on Mars. There is no door that leads to somewhere else. Every door leads to another room in the same machine. And inside that machine, the question of authority becomes uniquely charged. Who decides how to ration power during a dust storm? Who decides which system gets repaired first when 2 fail simultaneously? Who decides whether a crew member showing signs of depression should be relieved of critical duties? And who takes over those duties in a crew of 4 where everyone is already overloaded? On the International Space Station, mission control in Houston or Moscow provides operational authority and arbitration. Disagreements between crew members can be mediated by ground teams with broader perspective and established protocols. On Mars, with communication delays of up to 24 minutes each way, real-time mediation from Earth is impossible. The crew must govern itself, and self-governance under permanent existential pressure. With no external authority to appeal to, no court, no ombudsman, no option to request transfer, creates social dynamics that no analog mission has adequately tested, because every analog mission operates under the implicit authority of the space agency running it, and the legal systems of the country hosting it. On Mars, those implicit structures would be absent. The crew would be the most isolated self-governing community in human history, making life and death decisions by consensus or command, with no recourse if the process breaks down. The communication delay adds a layer of isolation that is qualitatively different from anything experienced on Earth or on the International Space Station. A conversation with family on Earth would involve speaking a sentence, then waiting between 8 and 48 minutes for a reply. Real-time dialogue is physically impossible, and video calls as we know them cannot exist. Every interaction with loved ones becomes an exchange of recorded messages, delivered with the emotional cadence of letters rather than conversation. For parents separated from children, for partners separated from each other, for anyone whose emotional well-being depends on the rhythms of genuine human connection beyond the habitat walls, this delay transforms communication from a lifeline into a reminder of distance. Over months and years, this communication structure changes the relationship between settlers and Earth. Earth becomes abstract. The people on it become increasingly disconnected from the daily reality of Martian life. Settlers would develop their own routines, their own social norms, their own interior culture shaped entirely by the conditions of confinement. Earth-based friends and family, unable to share the lived experience of the habitat, would gradually become voices from another world in the most literal sense. The psychological literature on isolated communities, from Antarctic research stations to submarine crews to remote military outposts, consistently documents a phenomenon of social drift, where the isolated group progressively identifies less with the home culture and more with the immediate community of shared experience. On Mars, this drift would be permanent and deepening. Depression is a near certainty in some crew members over multi-year durations, not as a personal failure, but as a predictable neurobiological response to chronic confinement, sensory deprivation, social limitation, and the absence of environmental novelty. The human brain requires a certain threshold of new sensory input to maintain normal emotional regulation. Below that threshold, dopaminergic and serotonergic systems begin to downregulate, producing symptoms that overlap with clinical depression, loss of motivation, emotional numbness, difficulty concentrating, disrupted sleep, and social withdrawal. On Earth, depression is treated with therapy, medication, lifestyle changes, and environmental modification. On Mars, the first-line treatment, environmental change, is unavailable. Medication supplies are finite. Therapy from Earth-based psychologists would be conducted through time-delayed messaging. The crew would be largely responsible for managing their own psychological health, using whatever coping resources they brought with them, in an environment that systematically undermines those resources. Now layer the physical and psychological burdens together, because they do not operate independently. A body experiencing chronic bone loss, muscle weakening, and possible cardiovascular deconditioning is a body that feels wrong. Subtle changes in physical capacity, getting winded more easily, feeling unstable on your feet, experiencing joint pain that was not there 6 months ago. These physical signals feed back into psychological state. You feel weaker, you feel less capable. You notice that your body is changing in ways that moving to a new planet was not supposed to cause. The mirror becomes an adversary. The daily exercise regimen, already monotonous, becomes tinged with anxiety about whether it is working. Physical decline and psychological decline reinforce each other in a feedback loop that is well documented in aging populations and long-term hospitalized patients on Earth, but has never been studied in the context of permanent, off-world habitation. Medical capability on Mars would be profoundly limited. The Habitat Medical Bay would contain a finite supply of pharmaceuticals, basic surgical tools, diagnostic equipment, and perhaps a compact imaging system. It would not contain an operating theatre, a blood bank, a pharmacy with full formulary access, or specialist physicians. The crew's medical officer would likely be a physician with broad training but no ability to perform complex surgery, manage rare conditions, or treat advanced disease. A dental abscess, an appendicitis, a kidney stone, a fracture from a fall in the habitat, any of these would be managed with whatever is on hand. A condition requiring surgery beyond the crew's capability, a ruptured appendix, a severe traumatic injury, an aggressive cancer, would be untreatable. Evacuation to Earth takes months under the best orbital alignment and is impossible under the worst. For some medical emergencies, the outcome on Mars would be death from a condition that any emergency room on Earth could treat in an afternoon. This medical reality imposes its own psychological burden. Every crew member would live with the knowledge that a serious illness or injury could be a death sentence. This awareness, even when pushed to the background of daily consciousness, colours every activity with a faint tint of existential risk. Climbing a ladder to repair a ventilation unit is not just maintenance. It is an activity where a fall could produce a fracture that cannot be properly treated. Eating food from the hydroponic bay is not just a meal. It is an act of trust in a food supply system where contamination could introduce pathogens that the habitat's limited antibiotics might not defeat. The cumulative weight of all these burdens, physical, psychological, medical, social, environmental, is what separates Mars habitation from every other extreme environment humanity has occupied. Antarctic researchers rotate home after a season. Submarine crews surface after a deployment. International Space Station. Astronauts return to Earth after 6 months. In every case, the human body and mind endure the hardship because it is temporary, because Earth and its restorative abundance are waiting at the end. Mars offers no such promise. The hardship is the destination. The confinement is the life. The biological decline is the trajectory. And the planet outside the habitat walls offers no comfort, no restoration, no relief, only the same silent hostility it has maintained for 4 billion years. Here is where we must confront the deepest truth this story has been building toward. The phrase, living on Mars, contains an assumption so embedded that most people never examine it. The assumption is that the word living on Mars would mean something recognizably similar to what living means on Earth. It would not. On Earth, living means breathing without thinking about it. It means drinking water from a tap. It means walking outside and feeling the sun on your skin without calculating your radiation dose. It means eating food that grew in soil under open sky. It means hearing rain. It means standing in wind. It means sharing a city with millions of strangers, any of whom you might meet tomorrow. It means knowing that if you are sick, a hospital exists. If you are lonely, a friend is a phone call away. If you are bored, the world is full of places you have never seen. Living on Earth is embedded in a web of biological, social, and environmental support so vast and so deeply integrated into every moment of experience that we do not perceive it as support at all. We perceive it as reality. We perceive it as normal. On Mars, none of this exists. Every element that makes life feel like life on Earth would be absent or artificially simulated. Air is manufactured. Water is recycled from waste. Food is grown under artificial light in a closet-sized module. The sky is a rust-coloured haze seen through a small viewport or not seen at all. Social contact is limited to the same handful of faces, year after year. Medical care is whatever fits in a cabinet. Exercise is a treadmill in a corner. Entertainment is whatever digital files you brought, eventually watched, read, played, and exhausted. The sensory world shrinks to the dimensions of the habitat. The emotional world shrinks with it. This is not a frontier. A frontier implies open space, new territory, the possibility of expansion and discovery. Mars offers none of these to a daily inhabitant. The daily inhabitant is sealed inside a pressure vessel, maintaining the systems that keep the pressure vessel functioning, eating food grown inside the pressure vessel, breathing air recycled inside the pressure vessel, and sleeping inside the pressure vessel while outside the pressure vessel. A planet of incomprehensible hostility waits with the patience of geological time. The frontier is not out there. The frontier is the 6 inches of engineered wall between your bloodstream and the vacuum. And yet, humans may still go. Perhaps humans should go. The impulse that drives our species toward hostile frontiers is not rational in the narrow sense, and it does not need to be. We crossed oceans in wooden ships that killed half their passengers. We climbed mountains that offered nothing at the summit, but wind and the view. We descended into caves, sailed into storms, walked into deserts, and launched ourselves into orbit on pillars of controlled explosion, not because these things were safe, but because something in the human animal needs to know what is on the other side. Mars is on the other side. It is the next place, and some people will go there, fully aware of what awaits. but they should go with honesty. They should go with the clearest possible understanding that what they are choosing is not a new life on a new world in any sense those words have ever previously meant. They should go knowing that the images of Martian sunsets and open landscapes are postcards from a world that will never welcome them. They should go knowing that their daily existence will bear more resemblance to operating a submarine than to homesteading on a prairie. They should go knowing that their bodies will change in ways that cannot be fully predicted, their minds will be tested in ways that cannot be fully prepared for, and their connection to Earth will fade into a thin thread of time-delayed messages stretching across a void that grows wider every day. They should go knowing they may never come back, not because the rocket does not exist, but because after enough years at 0.38 G, their bones and their hearts may no longer tolerate the world they came from. The real shock of living on Mars is not any single danger. It is not the radiation, the dust, the cold, the airlessness, the toxic soil, the equipment failures, or the isolation. It is the way all of these things combine into an environment where ordinary human life becomes impossible and is replaced by something else entirely. Something that looks less like settlement and more like permanent survival management. Something that looks less like a new home and more like a life support experiment conducted on hostile ground, with no control group, no exit protocol, and no guarantee that the machinery will hold. Mars does not hate us. It is not cruel. It is simply indifferent in the most absolute sense the word allows. It is a world of cold rock and thin carbon dioxide and ancient silence, and it has been that way since long before anything alive existed anywhere in the solar system. It does not resist human habitation out of malice. It resists it because it was never shaped by the forces that make habitation possible. No magnetic field to block the charged particles, no thick atmosphere to hold warmth and pressure, no liquid water on the surface, no oxygen in the air, no biology in the soil, nothing. Just a planet-sized monument to what a world looks like when the conditions for life never quite came together, or came together once and then drained away over billions of years into the vacuum of space. To live there would be to exist inside a bubble of Earth, carried across the void and set down on alien ground, then maintained by hand against everything the ground can throw at it. It would be to spend your days keeping the bubble intact and your nights sleeping inside it, knowing that the bubble is aging, that its seals are wearing, that its filters are clogging, and that the planet outside is the same as it was yesterday and will be the same tomorrow and will be the same a million years after the last human leaves or the last habitat fails. And it would be to carry, somewhere beneath the daily routine of system checks and filter replacements and crop rotations and radiation logs, the quiet knowledge that you chose this, that you left behind a world that gave you everything for free, air and water and warmth and sky and the sound of wind through living trees, and traded it for a world that gives you nothing and never will, and that the distance between those two worlds is not just measured in millions of kilometers, but in the growing silence between the messages you send home and the replies that take a little longer each time to feel like they are coming from the same reality you once belonged to. That is what living on Mars would actually be like. Not a new beginning on a new world. A permanent vigil inside a fragile machine, on a planet that never stops reminding you that you are not built for this, that nothing you are was built for this, and that every breath you take is a small mechanical victory against a silence that has lasted longer than life itself.